This video demonstrates some of our research in the area of privacy-protected video surveillance system. Our system is developed for complex indoor environments with walls, partitions, furniture, and human traffic. Some areas in the environments, like the red area, are of high security values and must be protected under surveillance at all times, while other areas, such as those green areas, cannot be under surveillance due to privacy concern. Our first research accomplishment is to develop software for optimal camera placement that can simultaneously maximize the surveillance coverage and minimize the cost of building the camera network. For any given 3D environments and human traffic flow, our software can derive the optimal number of cameras needed, their positions, and their angles suitable for the target surveillance application. As our system offers different levels of privacy protection to different individuals, we need to have a mechanism to identify each individual. Using biometrics such as face and iris, we have developed an anonymous biometric access control system to identify individuals' protection level while protecting their identity. The biometric signal is first captured at the entrance area, encrypted for privacy protection, and sent to the main server for authentication. The server and the sensor then engage in a secure multi-party computations to verify the protection level. The whole procedure, however, guarantees that the server has no knowledge of the biometric signal and thus can never know the true identity of the person entering the environment. We have also built a camera network that consists of both regular and thermal camera. Different cameras coordinate with each other so that object can be tracked throughout the whole environment. The object tracking allows us to provide the desired privacy protection level at all times. Image obfuscation is applied to use black box, noisy silhouette, or even complete object removal for privacy protection. It is important to know that we never destroy the original video surveillance footage. By using a high-capacity data hiding technique, the original image is securely embedded inside the original video and can be retrieved with a user-defined password. The data hiding scheme also produces a single video in standard compression format, so no special system is needed to store or view the video. In the first demonstration, we are going to show our camera placement software. It is development using the MATLAB scientific programming environments. The first screen shows our environment construction graphical user interface. Different obstacles like columns and furniture are first drawn. As cameras are likely to run at the perimeter of the environment, we draw the red lines to restrict the possible locations of cameras. Then we enter the second phase of simulations. We first generate the grid points which are needed to run our discretized integer programming optimizations algorithm. Then we adjust the heights of the room to make the simulations three-dimensional. We then specify the distributions of human traffic. The GUI allows us to play attractions where people may gather and doors where people entering and leaving the environments. Then we generate the traffic by using a 2D random walk traffic generator. The generated traffic map shows the white areas to have the highest density of traffic. Finally, we run our optimizations algorithm. The output is a set of camera positions and orientations as specified by the small blue triangles. 8 cameras are used in this example, as we have chosen to increase the robustness by having at least 2 independent camera views on all objects at all times. Other target surveillance goals can also be specified, and different number of cameras will be used. We now show an actual demonstration of our entire system in our laboratory. At the entrance, there is a small biometric reader to identify the face and implement our anonymous biometric access control system. The encrypted face image is sent to the biometric server, which verifies the membership of each person entering the room without knowing the true identity of the person. As shown in the video, the first person entering the room is not a member, while the following 2 persons are both valid members whose privacy will be protected in the surveillance video. Now we switch to what's happening inside the room. The bottom right is a video showing what is actually happening inside the room. The 2 videos on the left shows the user interface of our privacy system. The first person entering the room, being a non-member, does not have any protection. The green box shown in the 2 camera views shows that our object tracking module is working and functioning well. The next person entering the room is protected by a red silhouette. Different colors are used for each different person, demonstrating that our tracking is robust under occlusions and object movement. The last person entering the room is protected by a blue box. Note that in our GUI, different obfuscation methods can be changed on the fly, from black box to silhouettes to full object removal. In the final demonstration, we want to illustrate the concepts of hidden data or watermark in preserving privacy data. The privacy object is kept as an encrypted watermark which is embedded inside the modified video. After proper authentication, the watermark can be retrieved, decrypted, and recombined with the modified video to recover the original surveillance footage. Let's see how it is done in software. First, we select the video bitstreams of the modified video. Without the password, only the modified video can be seen and no access to the original video is provided. By entering a proper password, all the modifications can be reversed, exposing the original videos on the right-hand side.